Okay, hello everyone. So today's topic, we're gonna go in depth into simulation, complete search, and brute forcing, which are essential like beginning algorithms that you'll need to know for computer programming. But before all that, we're gonna do a review of yesterday's homework, and then we'll go into these different we'll go into these different topics and their application to USACO problems, and then I'm gonna give you guys your homework assignments. Okay, let's review our homework. Okay, white sheet. So here, let's look at this problem. Basically, you're given the coordinates of a table, which are like the bottom left coordinate says has 0, 0, okay? And then the bottom left corner of a white sheet on the table is x1, y1, x2, y2. And then there's two other black sheets, which we're given the coordinates of the bottom left and upper right as well. So what it's saying is we need to determine if some part of the white sheet can be seen from above. So if there's any part of the white sheet that's not blocked, then we print true. Otherwise, print false. Okay. So I'll let you guys think about this for just a little bit until like 10:09 or something, but yeah. And then I'll go over the solution. Okay, I'm just gonna head straight into the solution now. So basically what I did here, so I created a struct in order to store these bottom left coordinates and the upper right coordinates. And I also had an area function that returned the area of these specific recs. So I could store these. And I also had a function that automatically calculated, and I made it public so we could access it from the main. And I created three different of these rec data types, read in the values. And then I basically said, okay, so depending on the intersection, I will cut my rectangle area. So this method cuts the white sheet based on the dimensions of B. So like, for instance, if B is on the left side, then A's left coordinate, A dot x1 is going to be greater or equal to B dot x1. And then B dot x2 is, which is the black sheets. Okay, B dot x2 is going to be greater or equal to the white sheet's left coordinate, which is A dot x1. And then B dot y1, which is the black sheet's lower y coordinate, is going to be less or equal to A dot y1. And then similarly, like B dot y2 is greater or equal to A dot y2. You just need to make sure that these line up, and they do. It's greater than A dot y2. And whenever this case is valid, we're just going to change the coordinates to reflect it. We're going to cut the coordinates of the white sheet to match. So A dot x1 becomes B dot x2. So basically, we're just slimming the white sheet's coordinates down like this. We're cutting it. So now this is all that's remaining. And then we're going to use this map function if B covers it entirely cover it up, instead of just cutting it partially. But eventually, like, what all these functions are going to do is just going to cut down the white sheet entirely until like here, this is going to cut down, like this portion is going to get cut out. this portion's gonna get cut out. Like we're just cutting out like different portions of the white sheet, and depending on like what areas are remaining. Then in the main function, I'm gonna print out no if the remaining area is zero, and then like yes if there is no remaining area, because that means that there's still some white sheet showing after all these operations. So okay.
All right, so next we'll go over our second problem from the homework, which was from the USACO 2018 January contest. Bronze problem 1, it's called block billboard. So let's read the problem quick. So Bessie the cow used to have a nice view from her barn looking at across the road at a set of 2 billboards advertising delicious looking cow feed. Unfortunately, one of these billboards has recently been updated, so it now advertises Farmer Larry's lawnmowers. Bessie is not a fan of lawnmowers since their only purpose is cutting the grass. So again, this is just like the story part for the first paragraph. So fortunately, the remaining cow feed billboard is situated in front of the lawnmower billboard, potentially obscuring it. So Bessie determined to remove the offensive lawnmower billboard completely from review hatches a risky plan. She wants to steal a rectangular tarp from the barn and sneak out late at night to cover the remaining portion of the billboard so she can no longer see it. So given the locations of the 2 billboards, please help Bessie compute the minimum area of the tarp she will need. Since the only tarps available in the barn are rectangular in size, Bessie observes that she may conceivably need a tarp whose area is slightly larger than the exposed area of the lawnmower billboard, as illustrated in the example below. The tarp may only be placed such that its sides are parallel to the other billboards. So basically in this problem, as you guys we just read, is we're given the locations of like 2 relative locations of 2 billboards, and we want to cover up one of the ones completely. Let's say this is the lawnmower billboard, and this is the billboard that she likes. We want to cover this entire remaining area. So we can't just pick something that's like this, for example, because it wouldn't cover the rest of the area. So we need to cover something that's a big, like covers the entire thing. So that's what it means by like, we need to be able to get something that is a little bigger in size. And also it tells us that we can't have like a diagonal billboard because that would just complicate the problem more, right? So for the sake of rectangular geometry, we're going to be sticking to this kind of like architecture for the problem. So in the sample input, you could see that it gives us the bottom left and top right corners of each billboard, and then we just have to get the area of the remain, like what we need to create for a lawnmower billboard. All right, so let's take a look at our solution here. So like I suggested yesterday when we were doing the rectangular geometry section, you should use casework. That's really helpful. So case 1 is the rectangle has all 4 corners covered. In that case, we don't need to cover anything, right? Because the billboard is covered completely and the remaining area to cover is 0. Another case is in which 2 corners are able to be covered. So you have something like this maybe. In that case, we have to remove the intersection of the rectangle over here. So just discount this. And we just have to create a rectangle around this. So the remainder of the area just needs to be covered over here. And the third case that we can have is if fewer than 2 rectangles are covered. So either 1 rectangle or 0 rectangles. So notice that whether we have one corner of the billboard covered or we have none of the corners covered, we're going to have to end up covering this entire height, and we're going to have to cover this entire width as well. And this is because regardless of whether we have 1 corner or 0 corners covered, we're still going to have to cover the entire height and width. So basically we have to cover the entire rectangle. So these are kind of like the cases that we have over here that we have to determine to basically develop our algorithm on how we're going to cover the billboard. So these are the different possibilities. So in this problem, I used ifstream upstream just to show you guys like how it works, but basically it's the same thing as file IO from the free open stuff like that you write over here. So basically you just have to use fn instead of cn if you use upstream. This is just for file IO, by the way. So basically what this function is going to do, I created a function, is I'm going to find out the amount of corners that are covered. And it's basically just going to find out if the corner is in range, like the corner. It's going to, the if statement is basically going to check if like the corner is inside the other billboard. So this is long if statement, and if the corner is covered, then you return true, otherwise you return false. So that's just a reference function I'm using, so it can kind of let you guys understand the code better. So in our main function, we're going to read in the input of all the bottom left and top right corners of both billboards. We're going to have a variable that counts how many corners are covered, so we can kind of use this algorithm that we described earlier for the corners covered. And then I'm just going to check if each corner is covered from the billboard. So here are the different cases. You guys can look into that, but basically we're looking at the bottom left and top right corners of each rectangle. And using this information, we're going to determine how many corners are covered total. And so either between one and four, right? So after that, we're going to get the lawnmower area, because in case that we are on like case 3, right? We have to cover the entire rectangle, and we're also going to get the intersection area, which is going to help us for case 2. And then this just code is just repeated because the code was a little long, but yeah. So if there was no intersection area, then that means that basically the rectangles weren't touching, right? So that means we need to just print out the lawnmower area because we need to cover the entire lawnmower billboard by ourselves. That's case 3. So otherwise, if we have 4 corners covered, we don't need to cover anything because the current billboard already obscures the lawnmower billboard. So the leftover area is 0. And lastly, there's 2 corners covered, like over here. Then we just have to subtract the intersection area because, like, for example, again, we have something like this. It's just the area of the lawnmower billboard minus the intersection is what we need to cover up, right? So that's why I'm just doing lawnmower area minus intersection area. So that's basically the idea behind this problem from homework. All right, so next I'll let
Okay.
Brandon go over time complexity again from yesterday's topic. This is one of the most essential topics, so we want to put some more time towards it.
Yeah. Okay. So I'll just be reviewing this concept right here. Some key tips. Whenever you're worried about runtime for USACO specifically, you want to be worried about the worst case runtime, which is big O. I know I briefly introduced you guys to theta and omega, which are like different ways to measure time complexity, but you're always worried about the worst case. So you want to worry about big O when doing USACO problems. And then when you have your algorithm determined, make sure that with the input size, your actual algorithm will run less than 5 times 10 to the 8th operations before you actually implement it. So you know if you actually have a reasonable algorithm or not. Okay, so when you're doing asymptotic analysis, which is your way of looking at a function and determining its worst case time complexity, think of n as approaching infinity. So you can't just like say, oh, n equals 1, so like this function could end early if n was 1. Like you can't think of it like that. You have to think of it as n being a very large number whenever you're analyzing these functions. And then finally, this might be intuitive, but you're always trying to use the fastest algorithm. So before thinking about like, oh, like let me use this like n factorial like algorithm, you want to think about what are some constant time algorithms that I can use that allow me to solve this? Like, can I use certain data structures, like an array to receive certain index, or can I use a key to, I mean, can I use a map to find keys at constant time? Or any, once you like do your research, you might find some data structures allow for more efficient operations than others. So you want to look for which one will allow you to solve the problem in the best way. So yeah. Okay, so I have some problems here that might be helpful. So on the left, I just have a basic nested for loop. So for this, you're just iterating through the outside uh, n times, and the inside looks like you're also iterating by n. So this should be relatively straightforward. It's not really like there's no tricks being played here. It's just n squared because you got the outer loop being n, um, and you got the inner loop being n squared. And then on the right, this one could be potentially a little more complicated. But first, let me take a look at the inner loop, which is 1 through n. So I know the answer is there, but let's go through the thought process. So 1, 4, 2. So this is basically what k is. It's increasing like this. And then once it gets to n, that'll be the final one before it stops. So as I said last lesson, every single one is like, you can see it's like a geometric series, kind of like, because every single like every single term is well a difference, common ratio of 2. However, we're not adding these together. We're just determining the number of layers that we have here. So because we're not actually doing one operation, each layer we're doing one print. So we want to figure out the amount of the amount of multiplications and then multiply by 1, which is the number of prints, to find the worst case time complexity of this loop. So we know that each of them is 2 to the something. So 2 to the x equals n. And using log properties, if you just want to take log of both sides, log base 2 of both sides, we know that x equals log base 2 of n. And in time complexity, we can ignore the base when representing these, because that's inessential to like the overall like function shape. So now we know that the inner loop is log n. So we'll just take that into account. And then the outside, let's see. So this is essentially n minus n over 2, if we want to think about it like that. So 1 to n minus n over 2. So we're basically just going from 1 to half of n. But as I mentioned before, like if we're going 1 to n over 2, that's like n over 2 operations, right? We're adding n over 2 times in this loop. And then over here, we're starting from n over 2 and going to n. So that's also around n over 2 operations. We're just starting from the middle and adding a bunch of times till we get to n. So that's around n over 2 operations. So if we put this all together, then we can get something like this by multiplying. But as I mentioned before, you don't care about these constant time operations. I mean, you don't care about these constants when you're calculating your time complexity. So in the end, your time complexity of this function is O n squared log n.
All right, so next we'll be going over another essential topic from today, which is simulation. So this is kind of something that you guys will often be seeing inside competitive programming and problems in general, especially USACO. And you guys should be able to kind of figure out like your own algorithm and be able to code it up. So here's some tips for competitive programming simulation. So first of all, basically just follow along with what the problem is asking for. Be very clear on like what the problem is telling you, and kind of like that's how you're going to be able to develop your algorithm. So with this in mind, you can kind of think about like the kind of loops, data structures, and time complexity of your code. Less so time complexity when you guys are starting off like at lower levels of competitive programming. Like if you're doing USACO bronze, for example, you can care less about time complexity, but as you get to like higher divisions, silver and gold, you guys should definitely always keep in mind time complexity. They show up on every single problem.
I don't
So
know, actually, just a comment, like, actually the useful contest is getting harder. So I feel like you definitely do need to keep that into account these
and
days.
bronze, yeah. Usually, yeah,
So
by convention, people don't really mind it. As long as your algorithm doesn't have like too many, isn't too slow, you guys will get like at least some of the cases enough to pass. But yeah, that's just something to keep in mind, time complexity. So make sure you know about those when you're doing simulation problems, because simulation problems you often can like spend a lot of time writing the code. I mean, like the code is gonna like run really slow, is what I'm trying to say. So the algorithm should kind of follow what the problem is saying as a kind of like a hint to this, and it can be difficult to implement. Like just because you have an algorithm, it could be difficult to kind of translate that into code. So these are just some tips for simulation. So let's take a look at a challenge simulation problem here. So I'll let everyone read it and then I'll kind of explain the solution through it. So this is definitely a challenge problem. So just anything that you guys can think of is great. So I'll give you guys, so right now it's 10:26. I'll give you guys till 10:31 or 10:32 to kind of figure this out if you can, like anything, any clues on the data structures, the algorithms, time complexity, any way, any method of figuring it out. All right, so it's 10:31, so I guess we can kind of get the solution for this problem, explain it. So let's just read the problem quick and just basically understand what it's saying in case you guys couldn't figure it out. So essentially what's happening is we're given kind of a grid, a coordinate grid. Just to visualize it, I guess, as a coordinate plane that you guys see in math class, algebra 1, something like that. So a coordinate grid is telling us that it's only in the first quadrant, the positive side um, of the axis, which is helpful information because like you don't have to deal with negative numbers. So it's basically telling us there's n cows, n is less than or equal to 50. So that's something you should keep in mind. Whenever you see variables that are going to be read in as input, always keep them in mind, like n is less than or equal to 50, because that's what's being concerned with time complexity. So here we see that there's only 50 cows total, which is almost nothing. If you guys recall, in the USACO time limit, you can perform about 5 times 10 to the 8th operations, I believe. So if you have 50, which is 5 times 10 to the power of 1, that's like nothing compared to 5 times 10 to the 8th, right? It's a much, much smaller number. So that means that we can do some like pretty messy for loops and stuff like that, and like messy time complexity, and still be able to get full cases for this problem. Just like for you guys for reference, if you guys don't write an algorithm that's fast enough, like for example, if it's another problem and your algorithm is too messy and it gets the right answer, but it's not fast enough due to time complexity, you guys will get some test cases right, maybe, but it's just going to show like a red box with like a T inside it to show that like your algorithm took too long to run. So that's how you know if your algorithm is too slow. Okay, so in this problem, again, we're given 50 cows. It tells us that, I'll go over the sample input here. It tells us the coordinate and the direction that the cow is going. So for example, let's look at the 3, 5 cow. So 3 might be here on the x-axis and 5 might be here on the y-axis. And east is going this way. So this is the direction the cow is going to move. So it gives us the starting point, starting coordinate of each cow, as well as the direction that I'll move. And it tells us that every hour the cow will either continue moving or like eating the grass in itself. So I guess each point on this coordinate plane has grass on it, I guess you can envision. And it's telling us that every moment the cow that is on the coordinate plane, each cow is either eating a piece of grass on the coordinate plane, so it leaves the coordinate empty, and it keeps moving along, obviously, in the direction that, like, for example, this 3-5 cow is moving east. It's eating the grass from 3-5, and it's going to eat the grass on 4-5, 5-5, etc. as like the coordinates. And it's going to stop if the grass of the place it's at is empty. So let's say that this cow, we had another cow over here that's going north, right? So let's just call this like, I don't know, 6, 3. Let's just say that these 2 cows are over here. So if we look at this cow that's going upward or north, and we have this cow over here that's going east. Again, there's only north and east cows. There's no south and west cows, because then that would go to the negative axis, right? But that's not something that they consider in the problem. You're only considering cows in the first quadrant. So that's why there's no west and south direction. But so we have north and east cows, and they're basically going to eat the grass that's in front of them in their respective directions until they see something like until they see something empty. So if you guys can imagine this is cow 1 and this is cow 2. Well, cow 2 is going to eat the grass upward, and it's going to eat this intersection point between 1 and 2. It's going to get there first, right? Because it's closer. And over here, cow 1 is going to stop at that point because it can't eat the grass there. So like over here, it says every hour, each cow either stops so the grass in front of her current cell was eaten by another cow, which is basically what's happening over here. Cow 2 is eating the grass before cow 1. So cow 1 gets like an empty cell. So she stops right there. And otherwise, they'll continue going to eat the grass in the direction that they face. So that's what's happening over here. So it tells us that over time, each cow leaves like the empty cells behind her, which is basically what I just explained. And it's just asking us to determine the amount of grass eaten by each cow. And some cows never stop. So that's how we know that the cow must have eaten an infinite amount of grass. So for example, what we were looking at earlier, let's say that we have, I'll start off here. let's say this is cow 1, this is cow 2, and this cow 3. Then basically, we can see that this cow 3 is closer to the intersection point than cow 2. So that means I'll move across that point sooner and I'll eat the grass first. So cow 2 will be stopped over here, right? So let's just call this distance D. Then the total amount of grass that cow 2 eats is D. That's how what you would print out for cow 2. For cow 3, it's not going to stop at this intersection point. It's going to keep going. So let's presume that cow 1 is actually the first one to get to this intersection point, right? Let's call this D2. Then cow 3 is the one that's going to stop here this time because cow 1 is closer to the intersection point. So the amount of grass that cow 3 eats is going to be D2. And since cow 1 is never stopped inside this, it just keeps going, going, going. It's going to eat an infinite amount of grass. So for cow 1, you have to print infinity. So that's basically what this problem is giving us. It's giving us the cows, n, the number of cows, and then it's going to give us the data for which direction it's facing, as well as starting coordinate. And then we have to determine how much each cow is printing, how much each cow is eating for the grass. So for example, it's telling us that the east cow 3-5 is eating 5 total units of grass before it gets stopped. So let's take a look at how to solve this problem. Okay, so the key idea in this is to kind of think about your own algorithm and how you're going to approach the problem. So for me, notice how I kind of like I classified the cows as north and east, just as the problem has given me the characters inside the sample input of N or E. I can classify the cows as east or north. And that's going to help me basically be able to organize my data. And it's going to let me kind of use my for loops and be able to solve the problem. So then you have to choose your appropriate data structures, think about how you're going to store your data, develop an algorithm for it, and basically just apply simulation to what your algorithm was. So in this case, I'll explain my solution for this problem over here. This is definitely a challenge problem. It's rated very hard for USACO bronze problems, but basically I'll go over the solution here. So here's the data structures that I'm going to use. So I'll show the algorithm first and I'll explain what's happening here. So here's our coordinate plane, and I'm just going to draw some random cows. Over here, just draw some random cows, draw some test cases. Always draw it out when you're doing competitive programming. It'll definitely help you guys out. And what I'm going to basically do in this problem is we have to break it down, right? So I'm going to loop through the cows that are only facing north. I'm going to store the cows that are facing north. I'm going to store the cows that are facing east separately. Then I'm going to loop through the cows that are going north. And at the same time, I'm going to loop through the cows that are going east. Sorry, I've mixed up the directions, but basically I'm going to loop through the cows that are going north and east. And I'm going to compare each of them at their intersection points, basically, and determine who gets there first. Once I determine who gets there first, I can safely assign the amount of grass that the other cow is going to be like. If the other cow is going to be stopped, I can determine how much grass that the other cow ate, right? So basically, I'm going to be able to check every single possibility of north and east cows, where they intersect, who gets there first, and then I'm going to assign how much grass they ate in something like a map. So that's basically the algorithm over here. And I'm going to store the cows that are stopped inside a set so that I can kind of just tell that the cow doesn't need to like have any comparisons anymore. It's already done. So for example, if this situation over here is like an intersection point where the north and east cows are like moving and eating grass, then I don't want to compare like this randomly with another cow over here because like I already got a value that I assigned. So that's basically why I have that. So let's take a look at our solution over here. So here are the fundamental data structures that we're going to keep in mind. So grass eaten is going to store how much grass each cow is eating. So notice I have two variables here, like the two inputs that I'm storing inside this map. So the first is going to be basically we notice on the last, like the sample input, it gives us the direction. So like, let's say north, and it gives us the coordinate that at which it starts. So let's say 3,5, right? So it's going to store the coordinate as a unique value or a key in this map. And that's how we're going to classify the cow. We're going to classify the cow by the starting point that it's at. And the amount of grass eats is going to be the second value. It's going to be the value of the map. So that's going to represent the grass eaten. We're going to be able to classify how much grass that each cow is eating based on the coordinate. So we're classifying it by the starting point. So vector over here for the pair it's basically going to store the order. So Brian, could you go back one slide? Yeah, so over here you can kind of tell that the first cow is going to eat 5 grass and whatever. So basically I'm just going to store like the order at which we have to print the answer, because the order has to be specific. That's how you can tell like which cow ate how much grass. So the order has to be specific. So that's why I'm storing the order inside a vector. And over here, I'm going to do, as I said earlier, I'm going to store the north cows and the east cows. So the reason why I'm using a set here, if you remember, sets are just vectors without duplicates and without indexing, is that they're a little faster than vectors. And in this case, we don't need to worry about duplicates because there's no data that's going to go missing, because each coordinate is unique, right? So we're not going to have any duplicates anyway. So a set can be used because it's a little faster than vectors. So we're going to have what I said, basically, we're going to group the cows by north and east. And we're going to store, each of these is basically the coordinate. A pair is basically storing 2 values, the x and y coordinates, right? So I'm going to have the north and east cows, and I'm also going to have a disabled set. And this is basically going to be what I said earlier about if we don't want to consider the cow again. So for example, like if I'm having a north cow here and an east cow here, well, like if this north cow is going to get to the intersection point first, then the east cow will stop. And let's say I have another north cow here. Well, I wouldn't want to compare. I don't want this east cow to be able to start this future north cow, because this east cow already got stopped by the first north cow. So it doesn't make sense for me to like further consider this east cow when I'm doing my comparisons, right? So here I've been able to define my fundamental data structures for this problem and clearly define the algorithm. So all that's left right now is to code it up. So first, we're going to read in n, which is basically the number of cows there are, which was, I think, like 50. And we're going to loop through 1 through n. And we're going to define the variables that the input gives us. Each input has a direction, like, for example, north or east. And it also has a starting value again, so x, y coordinates. So that's why I'm defining char dir for direction, integer x and y for the x and y coordinates. I'm going to read it in as input. Then I'm going to push it back to the order, because that's the order that I want to print the answer, right? I want to be able to classify each cow in the order that the input was given. That's how the answer wants to be. That's the answer format. And here I'm going to do a trick. So I'm going to say grass eaten, which is the map, if you guys remember. So each cow has like a certain amount of grass eaten, right? So the cow at the coordinate x comma y as their starting point, I'm going to say they started off eating -1 grass. I'll explain why later, but basically I'm going to initialize how much grass each cow has eaten. So then I'm going to say if dir is equal to e, then I'm going to, that means that we know it's east cow. So I'm going to push it back to the set that contains the east cows. And otherwise, if it's not, the direction is not E, then we know it's a north cow. So I'm going to push it back to, not there, not the disabled set. We're going to push it back to the north cow set. So that's basically what I'm doing. I'm filling up my data structures so I can loop through them. So now it's going to be where we're just applying the algorithm that we talked about. So we've been able to establish kind of what's been happening with the simulation, what we're going to do. So now like we just have to write the code for it, right? So we're going to loop through all the north cows, and at the same time, we're going to loop through all the east cows. And using this, we can kind of do all the comparisons. So you might be thinking about the time complexity here. So n is less than or equal to 50. So essentially what's happening is if we're looping through every north cow and every east cow, we're basically having n squared operations, simply put. So n squared is going to be 50 squared, which is 2,500. And notice that this is, let's do some quick math here. So this is 2.5 times 10 to the power of 3, right? So 2.5 times 10 to the power of 3 is still nothing, because again, the USACO time limit is 5 times 10 to the 8th. And you can notice the exponent in the 10 is 8 over here, and over here is 3. It's way lower. So we know that our algorithm will run in time. So it's basically like an analogous to like an n-squared algorithm, which is fast enough for this problem. So after we basically determined that our algorithm will be fast enough to run within the time limit, then we start like continuing like coding it up. So if I'm gonna say if the cow that we're at is disabled, which means that like it's not like a valid, that means that the cow has already been stopped and we don't want it to be able to stop future cows because it's already been stopped. So it wouldn't make sense, right? So if the cow has been stopped, then like it means that dot count, which means does it exist inside this set? If the cow does not exist in this set, which means that like it hasn't been disabled yet. And we know that, okay, let me draw this out again. So let's say we have a cow going east and a cow going north, right? Well, the x coordinate of the east cow has to be, let me see, greater than north cow dot second. So n cow dot second is going to be, let me write this over here. So n cow dot second is going to be the north cow's y coordinate, right? So let me just classify this as like x2 comma y2. And let me call this east cow's starting coordinate as x1 comma y1. So basically, in order for this comparison to happen, two things must happen. So the y coordinate of the east cow has to be greater than the y coordinate of the north cow. Because if we have something like an east cow over here and a north cow that's above it, well, they're never going to touch each other. So we don't have to worry about that test case. So that's why I'm using the if statement to check if there's a comparison necessary. So the second condition that must happen is the x coordinate of the east cow has to be less than the x coordinate of the north cow. So that's why we're having that, because if we have a north cow here and we have an east cow here, again, they're never going to intersect. So there's no worry about that comparison, right? So that's basically what I'm checking. So we're checking over here in this if statement if a comparison is necessary. If it is necessary, here's what I'm going to do. So for just generally any case with the north and east cow, let me redraw that actually. So let's just presume that this is a north cow and this is an east cow. Then I'm going to calculate who gets there first. And the way you determine that is getting the distance between their starting point and the intersection point. So I'm going to calculate the difference in their x values. I'm going to call this dx. And I'm going to calculate the difference in their y value, which is dy. So if whichever is less represents who's going to get there first, right? So I calculate it here using dx and dy. I said if dx is less than dy, that means that, I'll draw that out. If dx is less than dy, this is called this dx and let's call this dy. Let's just call this the east cow and this is going to be the north cow. If dx is less than dy, then that means that the length that basically the amount of grass that it eats is going to be less. The east cow is going to get there first because dx, the total amount of x distance is less than the y distance. The east cow is going to get there first. So that means that the north cow is going to stop, right? If the east cow gets there first to eat the grass, that means that the north cow is going to have to stop. So that's why I'm setting the amount of grass it eats to equal dy because it's going to stop at that point, right? And I'm also going to insert the north cow into the disabled set over here because we know that since this north cow is going to stop, we don't want it to be able to stop other cows. So I don't want to compare cows that already stopped with cows that are like currently active and still eating grass. So then I'm going to break and basically we're done with that comparison. So otherwise, if this is not the case, if it's the opposite possibility, then dx is greater than dy. So let's say that this is dx and this is dy. The opposite situation will happen. The dy, the north cow will reach the intersection point first and eat the grass there. Therefore, the east going cow is going to be stopped. So grass eaten of east cow is what we're going to be able to determine as like a finite number. And we're going to insert the east cow into the disabled vector. So at this point in time, we've been able to establish how much grass each cow has eaten because it has either been stopped or it's either have continued going. So we've been able to assign values to every single cow and disabled every cow that has like that has been stopped basically. And now all that's left is to print out the answer. So we're going to loop through every cow inside the order, and we're going to class using like the map right over here. We can classify each cow from the X and Y coordinates. So using the X and Y coordinate of each cow inside the order vector, we're going to say if the grass eaten was -1, print infinity. Because what's happening is every value inside the map has been changed over here. The amount of grass that each cow has eaten has been changed. But remember like the unchanged values, right? They will remain -1, which I talked about like way back in the earlier in the problem. If you guys remember, we initialized it to -1. So if the grass eaten by a cow is still like hasn't been changed, that means that it's never been stopped. So that's why we're going to print infinity over here. If there is a value of the amount of grass eats, we're just going to print it out, and that's about it. So this is a challenging simulation problem for you guys. So just be able to read the problem and then think about the algorithm carefully. It might take you quite some time. So in this context of the USACO contest, the problems are you usually have like 3 hours to solve 4 problems. Or in the US Open contest, you have 4 hours to solve 3 problems or 5 hours to solve 3 problems. So you guys have quite some time to think about this. But in this case, we're just explaining our solution here. So next we can go on to complete search. So Brandon will go over that.
Okay, I can go over this. So what complete search is we search through all the different possibilities in a solution space. So what I mean by that is like, we just iterate through every single possibility and see which one's the correct one, for example. And this is also known as brute forcing. And usually, you only it's easy to implement a lot of the time, but sometimes like the time complexity can be slow. So it's not like extremely creative or anything. You're just like looking through every single like possibility. So it can get some easier problems done, but like in terms of the higher level, it's not going to run in time. But it's still useful to know. Okay, so first let's look at this. Write a function that finds the maximum sum of a continuous subsection of size length from the input vector. So I'll just give you guys like 20 seconds to look at this, but yeah. Okay. So if you guys have any thoughts, leave it in chat or say something, but I'll go over. So nums is a vector that we're using right now. Okay, and the vector is mutable, meaning we can change the size. So it's fine if we push back different things that we read in. So size len, which in our case is basically just n. So for len, we're gonna push back all the different numbers into our vector. And then our goal is to, oh, actually, okay, so n and len are actually different. So n is the amount of numbers we're reading into our vector, and len is the number we specify, which in this case, we're just saying is 5. But you can input anything. So for the specific length of a subsection, we want to find for this length of subsection, what would be the highest maximum sum inside our vector. So like if we had like 5, 12, 7, 9, then we want to find length 2, which one's the highest, we would just, what comes to mind intuitively? Okay, check this. Okay, 17. Check this, length 2, 19. Okay, that's currently greater. And then check this one, the final one, 16. And then since it's not greater, our answer is 19. So that's basically what a complete search algorithm would do. Just check every possible length to, and then see if just compare all of them to each other. And that's exactly what we're doing here. So if I bring that back, the array, you can see that data size minus len. So we're going from 0 to 2. We're starting from 0. Data size, so size is 4, and then length is 2. So we're going from 0 and then 1. And I believe this should be a less or equal to sign, but yeah. So we would go from 0, 1, 2, and then we would stop. And then inside what we're doing is we're starting from the current I, and then we're going from the current element plus the length. So we're just reading the elements inside this range and then adding it to our current sum. So for instance, since we're going to I plus len, for the first iteration, we're gonna be adding these two elements to current sum. And then the running maximum is here. The running maximum is here. So we're going to compare our current answers to the running maximum, and it is indeed greater to the smallest integer. So this will become 17. And then as I described before, we'll do the same thing. We'll look at this, 19 will replace. And then we'll look at this, 16 won't. So then we'll just print our answer. Okay,
Yeah, so
so
this
let
is
me,
a pretty simple problem.
I just want to see how much time we
So
have left. So
yeah,
yeah. Okay, I think, should we skip this one or no? Or should I go over this one? I think we don't,
I can just quickly
uh,
go over it. It will
okay,
only take
sure.
like a minute or two. Okay, so basically in this problem, what's happening, I'll just simplify it for you guys instead of having you guys read it. So let me annotate quick. So basically like a circular barn here, and we were given like the entry and exit points of like several different cows. And we have to, sorry, this is A, like the entry and exit, and we determine like how many pairs cross each other. So here we can see there's like an intersection point, right? We have to figure out how many cows cross each other. So in this context of this problem, let's look at the sample input quick. So it's going to
Oh,
give you guys the order over here. So it's going to tell you like A, for example, and it tells you A and B are crossing pairs. So I'll just use that information. So B comes next. It comes clockwise, let's just say. And over here, A is going to appear here again before the second B, and then there's going to be another value of B. Of course, there's values of C between it. So A, B, like C, C, right? But for the context of like figuring out this algorithm, we're just going to consider A and B because it tells us it's only crossing pair. The way we know it's crossing pair is we can just draw a line here and a line here, and we can see that they cross, right? So from the sample string, we've been able to determine kind of if they cross or not. And kind of you can just make this observation that if one of the letters appears between the segment of the other two letters, then we can just use that information to determine if it's a crossing pair. So since there's only one B inside between the A, that we know it's a crossing pair. So let's take a look at our code over here. So the key idea is to find out, in order to find out how many consistent pairs, think about the fundamental data structures again that you're going to use and iterate through it in a brute force method. So this is kind of like simulating what the problem is giving us, simulating our algorithm. So we're going to use file IO and we're going to store the positions that it starts at. So remember how in the string it gave you all the information to determine, oh, does one letter uh, show up between two other letters. So using that, we just have to get the index, right? So I'm going to store the positions of the start and end as like a pair. So start and end as a pair. And I'm going to read it in, and I'm just going to get the starting point and ending point of every single cow over there. And I'm going to set the amount of consistent pairs originally to be 0. Then I'm going to use my kind of brute force method. I'm going to loop through every possibility of cows because I want to compare A. Is A consistent with B? Is A consistent with C? Is A consistent with D? Is A consistent with any other letter in the alphabet to D, to Z, sorry. And then I'm going to start off again. I'm going to say, is B consistent with C? Is B consistent with D? I'm going to do this for every single letter. So that's why I'm using a double for loop here, a nested for loop. So I'm going to loop through the positions. And I'm going to just basically use this if statement to check if the pair is consistent. So does the x coordinates, this is start times match up in the y on the end times matchup. And if it does, then we add a bump up our answer and print it out at the end. So just like a quick review of how to use brute force in this problem. So here's like kind of like a USACO example that Brandon will go over for our topic today.
okay, so it's 11. So if you have something to do, please feel free to leave, but I'll go over this problem quickly and then go into the homework for today. So, basically, if we read the problem, there's n diamonds in a collection, and then basically, if any two diamonds differ by more than k size, then she will not want to include it inside a separate case. So there's a separate case, and if any two diamonds in this collection vary more than case, she won't want to display both of them inside that case together. So we want to determine the maximum number of diamonds to display in that separate case. And let's see how the input works. So we'll have n here, which is the number of diamonds. K is the maximum they're allowed to differ by if she wants to keep them in the same case. So just looking here, like a 6 and 1, for example, wouldn't be allowed to be in the same case because their sizes differ by more than K. So the way I would just like simulate this is like start from 1, and then I would look at everything after that. If the size differs more than K, then I won't want to include it in my case. So 6, I'm going to not include that. 4 is fine, 3 is fine, 1's fine. So in my current iteration, 4 are allowed in the case. Now let me start comparing at 6. At 6. So 1 differs by more, don't include that. This is fine, 3 is fine, this is not fine. So 3 does not replace. And basically, I just be checking every single one and comparing to every single one around it. And if it's valid, then I will, like, if the amount of diamonds allowed is greater than the current, like, running maximum, which I say a lot, then I'll replace it. Otherwise, I won't replace it. Okay, so let's look at the exact code. So as I said here, store the diamonds in a vector and brute force the possibilities of diamonds that can be stored in the same case. So for each, you're gonna iterate through the comparison diamonds, and then for this specific comparison diamond, you're gonna compare it to everything around it. And if this is valid, then we'll update our subtotal. So file IO here, read an input here, push the values into our vector, and then we have a running maximum here. So our current subtotal stores it for the specific iteration. And then for like, let's say, let's bring back the sample inputs. Let me just bring that back. 1, 6, 4, 3, 1. Okay. So for this, I will point here, and then we're gonna have J iterating through the rest of it. So J is gonna iterate through the rest of it. So first J is gonna be here. And if it's greater or equal to then, or if the difference is less or equal to this, then we'll update the subtotal. And in this case, we'll just basically iterate through each of them and check this. So this is fine, 1 is fine. So we'll update the subtotal. 6 is not fine though, because the difference is more. So we're not going to include that. And then diamond of J is greater than diamond of I, so that's fine. And the difference between them is less or equal to K, so that's fine. We'll increment. This will increment as well. The difference is less or equal to K, and then same here. So for this current pointer, our current answer is 4. Then we'll move it up to here. And then we'll try to do the same process over again. But then we'll see, like, we'll iterate through the entire thing and we'll decide that only this is valid. So we can't really replace because our current running maximum is higher than this situation. And we'll keep on going through and just updating, but eventually we'll find out that this is the maximum answer. So in the end, after replacing for each iteration the current maximum, we'll get that our answer is 4 for this specific case, and this will apply to any different input for this problem. So yeah.
Yeah, so these are all brute force problems over here, and just basically having to find out like what I want to do and just code it up. Like you don't really care about complexity too much, but like for the sake of these problems, but in the context of like a contest, you should definitely have it in mind. So next, Brandon will go over today's homework. So basically we just, yeah, you can go, Brandon.
Oh, you want me to go over it? Okay, so we basically just compiled a list of like a bunch of useful problems that they take into account this useful skill. I can just show one of them right
Yeah,
here, just so you get an idea. This is one that requires the use of just like complete search or like some basic algorithms that we went over today, and all of them are similar and just go over these
yeah,
algorithms.
the other two problems are some review problems as well. We've done some of these problems in class, in our past classes in our boot camp. So you guys can definitely figure it out. If you guys want to remember how to do these problems, then we'll go over it again tomorrow, and you guys can get some practice with what we've been going over so far.
Okay, so that's it for today. Thank you guys for
Yeah, thank you
coming,
everyone for coming.
and we'll see you guys tomorrow.